Let's take a few minutes and look at the results of these questions that involve not just binomial and geometric probabilities, but probability in general. There's even independence in here. There's and or and conditional probabilities. There's a lot of really good review here. So for part A of the question, the failure rate is assumed to be 15%. So what's the probability that the first 30 super igniters successfully launch rockets? Well, that means I need 30 successes all to occur in a row. But this word is very, very important because the super igniter failures are independent of one another. The successes then are also independent of one another. So I can calculate the probability by simply taking the success rate of 0.85 and multiplying it to itself 30 times. So the first launch has a success rate of 85%. And the second launch has a success rate of 85%. And the third launch has a success rate of 85%, and so forth. So because of the independence, I can calculate this as an and probability, and really all I need to do is take the probability and raise it to the power 30. So the approximate probability is 0.008. Make sure that you describe it or label it in context. So I just copied the words. The probability that the first 30 super igniters successfully launch rockets is this. So put it in context, show the work, give your answer. So the second one is pretty interesting. So given that the first 30 super igniters successfully launch rockets, what's the probability that the first failure occurs on the 31st or the 32nd super igniter tested? So essentially, given that the first 30 successful launches have happened already, so that's in the past, understand, because of independence, whether or not the first failure happens on the 31st trial, that probability is the same. That probability is not affected by the fact that we have already had 30 successful launches. So the probability that the first failure occurs on the 31st launch is 0.15. All right, so again, given that there have in the past been 30 successful launches, because of independence, the probability that the first failure occurs on the 32nd launch, well, here we have to be careful because we have had 30 successful launches. So to get to the 32nd launch to be the first failure, that means the 31st, the one before it, has to be a success. And then the 32nd one has to be the failure. So the success on the 31st launch is 0.85. The failure on the 32nd launch is 0.15. So I have to multiply those two probabilities together in order to calculate the probability of the first failure being on the 32nd launch. Again, notice this feels like a geometric setting because I don't have a fixed number of trials. Who knows how many trials I might have to go through in order to get my first failure. We're calculating the probability then that the first failure is on the 31st or the 32nd launch. And we're also using this idea of independence. And at some level, I'm not trying to get crazy with calculator formulas or calculator commands. I'm trying to use the words, the independence, the basic probabilities that are given in the problem in order to calculate this rather than getting all crazy. So look, in the end then, I want the probability that the first failure is on launch number 31 or on launch number 32, given that the first 30 launches are successful. Well, because of that independence, the first failure being on launch number 31 is 0.15. Well, the probability that the first failure is on launch number 32 is this probability right here, and I just took those two probabilities and added them together. This is an OR probability, so I can add because these are mutually exclusive of one another. There is no chance that the first failure is on launch number 31 and at the same time on launch number 32. That can't happen. These are mutually exclusive events. So this OR probability can be found just by adding these two probabilities together. So listen, if you could do the first question, part A, if part B was harder for you, then make sure that you use this strategy. If there's a part that's more difficult for you, don't spin your wheels on it, go on, because notice part C doesn't rely on part B. It goes back to part A. So if you could do part A correctly, regardless of B, you could still do C. So given that the first 30 superigniters successfully launch rockets, is it reasonable to believe that the failure rate of superigniters is less than 15%? Well, this doesn't use the word evidence, but essentially we're being asked to think about our answer in part A as a p-value. If something unlikely has happened, then maybe the assumption that we used to calculate that probability wasn't a good assumption. So, bottom line, the likelihood that the first 30 launches are successful is quite small. It's 0.008. That's from part A. Well, given, of course, that the true failure rate is 15%. Well, because this is unlikely, in other words, that probability is well less than, for instance, a significance level of 5%. If this is unlikely when the true failure rate is 15%, what we have evidence then, or we have reason to believe that the real failure rate of superigniters is less than 15%. So part C, you're not being asked to do a formal significance test. This question does not list a null hypothesis and an alternative hypothesis in a formal way. But what this question is asking you to do is to use a probability of an event to decide if the assumption on which that event is based is reasonable or not. This event, that the first 30 launches are successful, is based on an assumption that the true failure rate is 15%. Well, if that's true, the first 30 launches being successful isn't likely to happen. So that gives us reason to question that assumption. That means we have reason to believe that maybe the real failure rate is less than 15%. So going on to the next question then. I really like this question. It uses a two-way table again. It gives you a chance to practice calculating an and probability, an or probability, a conditional probability. It gives you a chance to think about independence. And then the very last part of the question, part C, is a binomial probability. This is a very recent AP exam question. So I would offer that the structure, the look and feel of this question is something that's reasonable to expect going forward. So part A of the question, what's the probability that the person selected will be someone whose response is never and who is a woman? No problem. Well, you want both of those to be true. So here is the never column. Here is the woman row. So our probability is the 0.0636 divided by the total. Although because the entries in this table are listed as decimals, the total is always going to be 1. So I know that here I took that entry, the 0.0636, and divided by 1. I'm not going to divide by 1 going forward. That's kind of silly, but I at least wanted to show it to you there. Instead of frequencies, if these were counts, you would have to be careful to take that value and make sure you're dividing by the total in order to find the probability. So don't just list an answer. That will not do it. It would be okay if you didn't list this, but it is very important to label this using probability notation, labeling the events using the word and if you don't want to use that probability notation, you can put in context simply by copying the words. The probability that the person selected will be someone whose response is never and who is a woman is 0.0636. You could just copy the words. So part 2 is an or probability. So what's the probability the person selected will be someone whose response is never or who is a woman? So again, I put it into the probability notation just to review it, never or a woman. So now I went and used a formula from the AP exam formula sheet. So an or probability is the probability of the first event plus the probability of the second event minus the and probability between those events. So I found the probability that the response is never, so that's 0.12, plus the probability of randomly selecting a woman, so that probability is 0.53. And then we have to subtract the and probability. The response is never and a woman. Well, conveniently, we already calculated that one up here in part A1, so I just recycled that answer here. So I added these and subtracted the 0.0636, and there's my answer. So that formula is available to you on the AP formula sheet. So something else, if you wanted to, you could simply list the probabilities that are represented by the or event, that the or event requires, and add them together. So the response is never or, the randomly selected person is a woman, you can simply add up these two values, which are the nevers, and then you want to make sure that you also include all of the probabilities that are in the woman row, but don't double count this one. So if you added the 0.0564 to the 0.0636 and the 0.1384 and the 0.3280, you could show those four probabilities added together. It will give you the same answer. That's an alternative way to show your answer there. But I wanted to use the formula as an excuse to remind you that formula is on the formula sheet. So number 3 is a conditional probability. So what's the probability the person selected will be someone whose response is never, given that the person is a woman? So the probability of a never response, given that the person is a woman. Okay, well that means that I'm only allowed to look at the woman row. So that means my new total is only 0.53. So that's in my denominator. And the numerator, I'm interested in the women that are also nevers. So that is the intersection of the woman row and the never column. That's the 0.0636. So that 0.0636 divided by the 0.5300, that makes exactly 0.12. So going on to part B of the question, for the people surveyed in this situation, are the events of being a person whose response is never and the event being a woman, are they independent? Justify your answer. Well, take a look. It's a yes or no question. You should say yes or no, and this time the answer is yes. These are independent events. Take a look then. This is a conditional probability. What's the probability of a never response given that someone is a woman? That probability is 0.12. Well, but look in the table. The probability of a never response in general is also 0.12. So you need to make that comparison in your answer. And again, you can use the probability notation or you can write it out in words. So the probability the response is never is 0.12. But notice above, we found that the probability the response is never, given that the randomly selected person is a woman, is 0.12 as well. Well, this means that the event being a woman, it doesn't change the probability that the response is never. Because of this, the events of being a person whose response is never and being a woman, those events are independent. Being a woman has no impact on the likelihood. It doesn't change the likelihood of a never response. So part C of the question then, if you read this part carefully, when you read this, you should recognize that this is going to end up being a binomial situation. So it says, assume that in a large population, the probability that a person will always take medicine as prescribed is 0.54. Now, the truth is they're just getting it out of the table. So always, ignoring men and women, always is 0.54. So that's the probability of always taking your medication on time. That's where that came from. So notice if 5 people are selected at random from the population, so I have a fixed number of trials. I have a sample size of 5. What is the probability that at least 4 of the people selected will always take their medication as prescribed? So support your answer. So support your answer means explain the model that you are using in order to do your calculating. So this was not required. So this section here, this first paragraph that I wrote, was not required in order to get an E on this section, but I wanted to use this to review. This is a binomial setting, so there are 4 conditions. So there have to be 2 outcomes. So either the selected person does always take medication as prescribed or they don't. So there is a fixed number of trials, that's 5. There is a fixed success probability. We are given that as 0.54, and we can act as if the selected people are independent of one another as long as there are more than 50 people in the population. So I'm checking the 10% rule here. The sample size is 5. 10 times 5 is 50. So we have to believe that the population is more than 50. But look, the stem of the question at the top of the page states that the survey is of a large group of men and women. So it says up here that this is from a large group of men and women, although notice they repeated it here in part C, assume that in a large population. So that wording suggests that certainly there's more than 50 people in this population. So independence is also reasonable. So I went ahead and described what my random variable represents. So X is a binomial random variable, so it represents a count. It is the number of people that say they always take medication as prescribed. It's the number of always, the count of always that we get when we're randomly selecting 5 people from this large population. So I'm using my binomial notation here. So X is distributed binomially with 5 trials and a fixed success probability of 0.4. It would be perfectly acceptable to write that out in words. You could say X is binomial. You could say n equals 5 and p equals 0.54. That is perfectly fine. So then I'm interested in the probability of at least 4 people selected will always take their medication as prescribed. So at least 4 includes 4 or 5 successes. So you could write that as the probability that X is greater than or equal to 4. Well, that's just the probability of 4 plus the probability of 5. And I found those 2 probabilities by using the binomial PDF command. So let me review that with you. So second variables, if you scroll down to binomial PDF, still going, there it is. So the number of trials is 5. My fixed success probability is 0.54. And I'm looking for 4 successes. So that's where I got the first probability of 0.196. There's the 0.196, that corresponds to the 4. And if we do the same thing for 5, that's where the 0.046 comes from. So I'll go ahead and do it again. Sorry, it's kind of slow. It takes a second on the calculator emulator to arrow down to the command that I want here. There it is. So it's still 5 trials, same success probability, but this time I want 5 successes. And that's where the 0.046 comes from. Again, I would encourage you not to use calculator speak or write down the calculator command that you are using. It is more important that you describe the model that you are using, that you use the word binomial. So at the very least, you use this notation. It might even be better to say X is binomial with n equals 5 and p equals 0.54. That's much better than writing out the calculator speak. So if you add those together, you get the 2.42. So, and again, I've rounded, so I put in the word about. You could use the word approximately. Another way to do this calculation, just something else to think about, you also have a binomial CDF command, so this is a good excuse to review that. Another way to find the probability that X is greater than or equal to 4, if I want to keep the outcomes, the probabilities for 4 successes and 5 successes, then I want to get rid of the probabilities of 3, 2, 1, or 0 successes. So I could think of this by taking 1 minus the probability that the number of successes, that X is less than or equal to 3. A less than or equal to specification for a probability in this binomial setting, I can use the binomial CDF command in order to calculate this. So, but it's important if you want to keep the 4 and the 5, the ones that you're eliminating are 3 or fewer successes. So if we go to the calculator, we could go to second variables and one last time, arrow down to the binomial CDF command. There it is. So we have 5 trials. Our fixed success probability is 0.54, but then notice I want to stop at 3. I want to find the probability for 0, 1, 2, and 3 successes, but I want to stop there. Those are the probabilities that I'm going to subtract from 1 so I can keep the probabilities of 4 and 5 successes. So this probability, highlight, paste, and press enter, you get 0.759. That's where my answer came from. So I have 1 minus 0.759, and I would encourage you to write that work. I would encourage you to write that. That work is important. So if you do that subtraction, then you get 0.241. Either of these answers would be perfectly fine. The only reason these answers are slightly different up here, I rounded both of these and then added them together. Here, I only rounded 1 time and then subtracted from 1. So again, either one of those methods would be perfectly fine, but in this question, it's important to represent the model that you are using. So because of the fixed number of trials, I know in this context that this is binomial. So either use the notation or not the calculator notation, either use this notation for binomial number of trials and success probability, or write it out in words, I'm using a binomial model with n equals 5 and p equals 0.54. It's important to be that specific and to communicate the model or the method that you are using.